Okay, so we can start. So this is the last lecture of my course. So I thought I will discuss some variations of percolation theory. Okay, there's the standard model, but then lots of different variations have been studied, and I thought I will discuss them, but not in great detail. You will have to read up about them in order to learn much more. And yeah, so this is sort of like an appetizer. I expose you to some topics, and then you have to, if you like them, then you have to study them by yourself a little bit separately. Okay. So the first thing I want to discuss is called invasion percolation. Okay, so the problem came up in the context of some experimental systems. There are rocks with oil, and people want to extract oil out of the rock. And the way they do it is to push steam from one side, and that pushes the oil out on the other side, which you can collect. This is the technique which is used in oil companies quite a lot, and this kind of oil bearing rock is called shale. It's a porous rock, in the oil resides in the pores, and you push steam from one side to get the oil recovery from the other side. Okay, but it turns out that people found that all the oil doesn't come out. Some of the oil remains in the rock, some 30%, which is quite a lot. And of course, the oil companies would like not to waste so much oil, and can we improve it in some way? And so some theoretical physicists were studying this problem, and they came up with a model of how the steam invades the porous rock, and that is called invasion. So here let us just say problem originates in real world problems. Push hot steam and fraction of oil remains, and these are the people Wilkinson and Williamson. And so they made up some model. Let us first discuss the model. And at any time the steam is pushed, and there is an advancing front of the steam. And this is a model. This is not the real rock, but what the different colors show is the position of the front at different times. Okay, or this is the kind of steam which entered earliest time, and this is the steam which entered before that, and so on and so forth. So you can see different parts of the steam. This is the front at some time, and this is the same front which was this is the steam which came later, and so on. Okay, so this is the model, and it's a schematic model, and but it was very interesting, because what happened was that they found that this system seems to generate these funny looking clusters, and these clusters have the geometry of percolation clusters at the critical point. So this system, you just push the steam into the rock, you are not changing any control parameter, and the system goes by itself into its critical point. So that was a very interesting and surprising observation. Normally people are interested in studying critical behavior in Ising model or whatever. So I go and I look at the temperature, then I tune the temperature, and then I get to the critical point. Then I have to I have to tune the temperature to a part in a million to be able to see very long range power law correlation structures. Otherwise, if you are slightly off the critical point, then it is not really per power law, there is a cutoff and all kinds of problems. And here the system is able to go to its critical point on its own. So it was called self-tuning to the critical point. Okay, so this is the dynamics of the system seems to reach a critical point without any external fine-tuning of parameters. And so this was the first example of what is called self-organized criticality. The system organizes, non-equilibrium systems organize themselves to be at their critical point. That is the general sort of scenario. And this was the simplest example. And so the way, so what this, the model in detail is the following, that the system consists of pores. There are necks between the pores. Necks have a distribution of sizes, some are very narrow, some are thick. And a narrow neck takes harder pressure to push fluid through, and a thick neck makes it easier to push through. Okay? So they just said that the distribution of neck sizes can be parameterized by a uniformly distributed random variable between 0 and 1. Okay? The distribution is not very important. All that matters is that some things are more bigger than others. And for our purpose, we'll just parameterize this is bigger than this by an interval which is 0 to 1. Okay? So all the bonds of the graph are given a random number between 0 and 1. So at any time, there is a fluid front. And there are lots of bonds available into which the fluid can flow. And they said that the fluid will go into the one which has the least pressure head. So the smallest number will push through, and the bigger numbers will not be pushed. Now this has gone through, then then the next smallest will be pushed through, and then the next smallest. But by the time you have done this, some new bonds have opened up, because once the fluid goes, then new perimeter sites are added to the cluster, and so the perimeter sites keep changing, and you keep on selecting the lowest, and that is how the growth occurs. Okay? Sorry? Right now it is a slow drive, so that the system.
I mean, like when you put something in 1 unit of time, it
pushes 1 unit.
Only 1 unit.
Yeah, only 1 unit. And then, so it really doesn't matter how short is the unit of time, but we are doing one at a time.
Because these different colors, then I don't understand.
So this is 10,000 versus 5,000 or whatever.
From the red one in the bottom,
Huh.
come there.
Uh,
First red one in the
yeah. So what may happen is that there was one bond which was kind of strong, but eventually it was selected. Once it was selected, then the water goes through there. One at a time. Sometimes it is stuck. The fluid front is stuck at a place because the local things are big, and then it grows there. But then that part gets stuck, and this part gets pushed through, and so on and so forth. Yes. No, so the dynamics is that we are applying the pressure slowly, and it selects the most pushy place. So it doesn't depend on what is the pressure, it just picks the one which is the most easy to push. This is the model, it is not real life. In real life, you don't wait forever and push so slowly that only one pore is invaded. Okay? But we are first studying this model, and then you can study what happens if you push several things together and so on and so forth. The point is, it will not change. We will appreciate that the answer doesn't depend very strongly on how much you push. Okay?
So how is the front defined? Like, is there a directedness there, or?
All the points which are where the fluid could go, which is the empty sites which have not been invaded, which are neighbors of the invaded sites. They are all called the front. Yes, sir.
So this whole idea of the advancing front penetrating the lowest
Huh.
sort of pressure pockets.
Yeah.
Can one think of this as like a very simple DIR model sort of a thing?
Something like that. No. All those models. So it is related to these other models. But let us not worry about other models which are similar to this. No. Of course, we should worry eventually. But right now, we are taking this on its own and seeing what can I say about it. Okay? And what's interesting about this model. So so it turns out that when people studied this, so first I told you that the cluster generated looks like the percolation cluster at the critical point, and then they looked at what bonds are selected. Then it turns out that the bonds selected have this random number assigned, which is a random, it's a random variable. Now you pick this one, now you pick that one. But all the numbers are less than one particular value. And bigger numbers are never selected, smaller numbers are selected, there is an upper bound. That upper bound is exactly PC of that square lattice, let us say here. So exactly all the numbers, if the numbers were between 0 and half, they will be selected. If the number is bigger than half, it will later on never be selected. So how come that happens? With a little bit of thought, you can realize what happens is that suppose I consider, I assign these the random numbers, and I pick all the numbers which are less than some value, some threshold A. And those bonds I color red, and the other bonds which are above A I don't color. Then if this A is equal to or above the percolation threshold, it will form a spanning cluster. Okay? So I take this. For every A above PC, it will form a spanning cluster. Now I take my starting point and I keep pushing. So the cluster of invaded sites, at some point, it will reach this red cluster. But the red cluster has the property that all the bonds there are less than or equal to PC. P star, A I called A. So then the growth will occur only on this infinite cluster. Other bonds will not be, because there is always a place where you can go which with the value is less than P. So it clearly goes to the critical point. Okay, is this argument clear? So the mechanism here of generating the infinite cluster is clear. So once the invaded site hits the spanning cluster, all further growth will be on the spanning cluster. Okay, so except in the beginning. It may happen in the beginning all the bonds have value bigger than 0.9, then I will select one of them. But eventually once you hit the spanning cluster, then every new bond selected will have a value less than PC. So then oil trapped in finite clusters cannot be recovered by this fluid displacement. So this was the explanation, that since you are pushing and there are always places the fluid can go, then there are pockets which are trapped and you cannot get. Maybe I do something else, I'll take the rock, I will powder it and then push, do something else. But at least this simple method of pushing steam may not work. Okay, if you are a technologist, you will say, no, I will do something. I will add some chemical to the steam so that something happens or something happens. So I'm not saying that this is the end of all possible ways you can recover oil. The oil companies will be very happy if you can do something else. But at least they are able to explain the basic phenomena that some of the oil gets trapped and some of the oil is pushed out. And you can kind of explain what fraction will be trapped. It's not such theory without any sort of...
Was it 30% in theta?
Yeah, 30% or so, that is correct. Okay, all right, so this was very nice. People liked this. So this was called self-organized. Invasion percolation was called tuning to its critical point. It was called self-organized, system organizes itself to be at the critical point. But there was a problem with this. The problem was that the dynamics I assumed says that the system picks the smallest bond and goes there, grows along there. So there is some kind of global interaction in the system. I have to look everywhere, find the smallest bond and push. But we imagine that in physics, interactions are local. They don't depend on what happens on Mars. I just do something locally and then see what happens. So people wondered if this kind of a mechanism can be obtained without invoking extremal dynamics, which is non-local. Can you get self-organization to critical point without invoking extremal dynamics? That was the question. And it turns out that it can be done. This was done in a very cute paper by Grasberger and Zhang. And they called it self-organized directed percolation. And the basic idea is the same. You do something or the other, and the system will go to its critical point. But we will not use extremal dynamics. We will use only local dynamics, right? So how can you do it? And let me sort of do it here.
Is the previous model, this extremal dynamics was dictated by what exactly? Because you had it at every time step you had on.
No, so it was, the idea was, it was called slow pushing. If you push oil very slowly, then it kind of can, what the model was, that every bond will eventually push through, but the waiting time in different bonds are different, and only the least one is selected because we are pushing slowly. But suppose I don't want to wait and I don't want to worry about extremal dynamics, then what can I do? So I will define the model. It was initially defined to be, it's not very clear that it will do something like what we want, but it turns out that it does. So they said take a line, at each site there is a random variable I start with. We just take them to be 0. I start with f of I at time t equal to 0 at all sites for all I. Okay? Now the dynamics of this model is very straightforward. If you want to get something at this time, we will take the same odd even lattice construction. So I will only draw one set of sites. Like that. So what I will do, I want to determine f at this site. It will depend only on its two downward neighbors. It will not depend on anything else. Okay? So f of I at t plus 1 is equal to f of I at I minus 1 at t and f of I plus 1 at t. And what they said, just select the min of these two numbers. Okay? So they were both 0, so min is also 0. Yeah. Okay? But so then they said that also pick a new random number. So this is called eta I at t plus 1. Eta I at t plus 1 is just a call to ran, and every time I call to ran, I get a new random number. It is uncorrelated random variables. And so I take the min of this and eta, and I take the max of that, bigger of these two. I pick, and that is my f. And I do it here, here, here. And then in the next one, I do it here. I take the min of these two and add a new random number and pick the max of that one. Just keep on going like this. Doesn't seem very well motivated. But what they found was that if you just do this and evolve it for a long time, the system goes into some kind of a steady state, by which is meant that when you go to 1000 or 1050, you cannot tell the difference. The system looks roughly the same. So they kept on invading this further and further, and they plotted x and probability that x is seen. So then I go to one line and I see how often is this value x obtained. X goes from 0 to 1, and they found the distribution looks like this. There is an upper threshold beyond which the x's are not seen. Okay? And sorry, I beg your pardon, I did it just the wrong way. There is a threshold below which the x's are not seen. Okay? And why does this happen? So this is x is the values, and this is the histogram of the observed values at a particular time slot.
X is F.
F. Yeah, sorry. Right. And this is F, sorry. Okay? So can we explain this one? And the explanation was given is fairly straightforward. It is again the same thing. I look at all the f's, at each side there is I look at eta. At each side there is an independent value of eta. Okay? Then I look at all the sites where eta is bigger than the percolation threshold. Sorry. Eta is less than the percolation threshold. Then there will be a percolation, and there will be a cluster of all the sites which are the red cluster, which is the set of sites where, so I go to a site and I try to draw a path downward. And there are many paths, and I will try to find the path for which the value of x, largest value of eta along the path is as small as possible. And that will be called the optimal path. Okay? So from each side, there is an optimal path which goes below. And the value of the value of f will be interpreted as the value of this optimal threshold bill. If I have that much money, that I can, at this point, the f is the value such that there is always a path such that I can go all the way down without taking a value which is bigger than this f. Okay? So I know that from here I can go to a path going down with a value which is, let's say, f1. Here there is a path which is value f2. What about this site? This site has a value eta. If eta is less than f1 or f2, then the lowest path is f1 or f2. But if eta is bigger than either of these, then my value is eta, because if I want to go below, I have to have value eta. So that is the rule. Min of these and max of that. So this procedure, this computes the function f recursively. And it's straightforward that it will compute it. Okay, there is not a problem. Each f is by construction the threshold for which a path exists down to 0. Only bonds along the path, everybody will have a value less than f. Okay, and now if f is very low, then there are no possible paths which go all the way to infinity, where everything is less than f. That is a percolation cluster. But if f is above Pc, then you will be able to find infinite paths which go all the way below, right? If the value of f is less than Pc, then there are no infinite connected paths where everything is less than f. So that is not possible. Everything will be above Pc. But how many will be above Pc? So then it says, sorry? F is just a local variable. It is the...
It's not P of f, right? It's P of f is seen in.
So this thing is P infinity of f, this function. is suppose the bond percolation was probability was f, then there is a fraction of sides which connect, and this side belongs to the infinite cluster if f is above this local value, but doesn't belong to the infinite cluster for this f, it's not equal to this value. So this curve is actually p infinity of f.
So it's not probability of f.
No, it's not the probability of f, it is the calculated value, but I have found, finally I just did the steady state and I found this. If I look at the system at time t, I will be able to calculate p infinity, or I will easily find the threshold because nothing below this is working. So I can determine PC. The system is able to determine PC, determine this function without my adjusting it in any way, in a single realization. In the old ways, I will generate a cluster at P and then count how many things are there and then generate again and then generate again. Here I am able to do the whole thing in one run, right? So this was very nice and interesting, and it's able to realize this extremal this self-organizing critical point without the extremal dynamics.
So the above f, that those numbers above f will exist in the steady state. That point which finds.
Yeah,
what
yeah,
what
yeah.
is the weight? How does the weight is determined exactly?
So very good. So suppose it so happens that I come here and this point is 0.9. Okay, the eta at this point is 0.9. Then the chances are that I will, when I calculate f, it will be whatever this stuff was, it will be fixed by my eta. Okay, but if my eta is low, then sometimes these guys will overtake that one, and the probability that other values will be bigger than your eta is the kind of function which gives this. Here, if your eta is 1, then nothing can be bigger than this. But if it is this one, then chances are that one of the two guys below actually has a bigger f, and so you will pick that number. And you won't get it at PC. So at PC, the fraction of sides is which will keep f is very small. It's not a very subtle argument. It is a subtle argument, but it's not a very difficult argument. So if once I have told this to you, you can convince yourself that this argument is good. It might take you 3 or 4 minutes to convince yourself, but you will be able to do it. It's not difficult, but it is not obvious. Okay, that is the ingenuity of Grasberger and Zhang, that they wrote down this particular model to calculate this function which shows this nice behavior. So in this problem, what that matters is only the ordering of eta. Some etas are bigger than others.
I want to plot P of f.
No. So I'm answering that question. So whatever eta distribution you pick, in the end you order them. And what comes into play is the percentile of eta. In this problem, this f is sort of the percentile of eta, which are above me or below me or whatever. And so you just change variables. You take your favorite distribution, convert it into a percentile distribution, and then use this theory.
Okay, so this will be just that distribution will convolution with this?
No, it's not convolved. It is just this p infinity is function of this f, which is the normalized.
For a new distribution, it is not just normal, right?
The normalized function percentile distribution goes from 0 to 1, and it is uniformly distributed by definition. Suppose I have a random variable which is sort of the height of people, and it has some funny distribution. If I convert it into percentile, in terms of the percentile, by definition the distribution is exactly this. 90% of the people are below 0.9. Okay, so it's a uniform distribution by definition. And we are using here this percentile of the things below, and that is how the argument goes. Okay. No, 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 it is not connected. So this is exactly the dynamics. It's, you know, it's one line. I don't know why they wrote down this thing. But now I am interpreting it in one way. I am saying that you can see, if I give you a value of f, calculated using this way, you can say that from this point there is a path going below where all the sites will have eta less than f, less than or equal to f. Okay? I have calculated the, I was given the value of eta at everywhere, and I am to find f everywhere. Okay? So finding f on the first line is easy, because these are all 0. This is just the local value of this variable. Okay? But if I want to find this one, then you look at the minimum of these two and you will go through that one and not the other one. But then this one may be bigger than both of these, then you got to take that number. So that's all. End of. There is a recursive way to find this threshold function f, which is a site dependent variable. Okay, so this is very nice and very unobvious. Of course, you can do this in 2 dimensions and 3 dimensions, that is not a problem. The same argument goes through unchanged. Okay? But when I was looking at this, I said, oh, this is very nice. It is a directed percolation, self-organized directed percolation. But can I get self-organized undirected percolation? Okay, with local dynamics. I will not invoke the extremal rule. Yes, sir.
So if you, the finiteness of, if you take a finite
Yeah.
set of numbers, so will it also match with?
Yeah, no, so this argument says that then the f's will be the f's on this finite graph. The definition of f is that it is the local threshold. It will not give p infinity for the infinite system, it will give p for my graph. Okay, it will have some finite size corrections or whatever. It exactly calculates the function you want for the system you have. Okay, but okay, so can I get a similar problem, but with undirected percolation? It will organize itself into undirected percolation. So we already did it with invasion percolation, but now we are saying we don't want extremal dynamics, we want local dynamics. Okay, but if you have local dynamics, then it turns out that this rule is not working, because you know the shortest, the path which has the least values of eta from a point may be some funny graph. There is no simple recursion from t minus 1 to t which will give you these extremal paths, which are the best paths I should take in order to get the least value of f. Okay, so how to do this? So this can also be done, but it requires a slightly more work. So now let me give you that definition. So this is called self-organized undirected percolation. Using local rules. Okay, so what we do now is to take, let us take a 2D lattice. Actually the argument works for all dimensions also here. So again, there is a value eta xy, which is an independent random variable at each site. I just throw it in. That's the quenched initial configuration. Okay. Now these values of eta are given at each site. I go to one particular point and I construct a path to the boundary. For all this path to the boundary, I will find the largest value of eta. Okay, and say that this path is characterized by that number, the largest value of eta I have to go through. Then take another path, it will have a different eta, take another path, that will have a different eta, and I take all possible paths and find the least possible eta of all paths. So that's my function f. It's the natural generalization of the function in the previous case.
Eta is on the bonds.
Yeah. No, we are just, you can vary, you can define the corresponding problem, it is not difficult, but let us work with this one. So I want to calculate fxy is equal to minimum over all paths starting at xy, ending at boundary, of maximum eta along path. So this is the maximum along path, and then you take minimum over all paths, and that's a particular thing which depends on xy. So this is the function I want to compute, and let us imagine that there is a person sitting at each of these nodes, and I ask him that, can you tell me what is the value of f at your site? So this guy can only see his own value of eta, and he can talk to his 4 neighbors, but he cannot talk to anybody else. Okay? So he says, I don't know what are all the paths, I have never gone there, so I cannot tell. So what can you say please about f? So he says that I can be sure that fxy is less than equal to 1 by definition. Everything is less than 1, even the maximum will be less than 1. This is what I can tell you. So in the beginning, this is the state. All the sites of the lattice, everywhere, we start with fxy equal to 1. Okay? Now we imagine that, of course, there is an external boundary to this, and at the boundary f is 0, because these sites, there is no eta. This is external boundary. And now the rule is that each guy knows what is the value of f which has been upper bound to f which has been reported by all its neighbors. Okay? And so it says f nu at xy is equal to min of f of neighbors, comma its own eta xy, and max of this. Okay? This guy says that, everybody is reporting correctly, nobody is cheating. So my value of eta is this. This guy tells me that if I go here, then there is a path to infinity which takes less than f1, which this guy is ensuring. If this f1 is bigger than my eta, then I just say, okay, I'll take f1. I go along this path and my best value is f1. If all the 4 neighbors are giving a number which is low and then my eta, then I say I cannot move unless f is equal to eta. So this is the rule. F nu is equal to minimum of all the 4 neighbors, and take your own eta and the larger of these 2. So at time 1, I will say that I can ensure everybody will update his numbers and say that now, based on the local information from my neighbors, I can say that, okay, I can take a path which is 0.9 and not 1. So how will this work? In the beginning, everybody was 1. This guy has a value, but all his neighbors are 1. So he'll just report 1, cannot change. Okay? But if you look at this guy, his neighbor is just there. So, and these guys are reporting 1. But he says, I can just go directly, so he will update his eta to his update the value of f to its own eta value. So the new f will inside be 1, but on the boundary they will be the local values of eta. Okay? Then I go to next time step. Then these guys in the next layer may also be able to update their numbers to lower numbers. And at the next time, the next layer, and the next time, the next layer. And I keep on doing it. Every time step, somebody or the other is able to quote a lower value. And that value can, then make some other person quote a lower value and so on. It keeps on going until it stops. Then it will not go on forever. At some time, all the f values reported will stabilize. Nobody is changing, then it doesn't change further. Okay? And so we have computed the correct function f using local rules. And this f will have the same behavior. It will have a lower threshold at PC, because below PC there is no connected path, right? So everything will go through, and we have managed to do it. The cost paid was that this function was not calculated in one go by one line, in that Grasberger-Zhang line. Here you had to keep on iterating and keep on calculating functions, keep on talking to neighbors, keep on updating information. In the end, you got there.
The initial setup of eta
Yeah.
is very hard, it seems, because you need to look for all paths and find the minimum.
No, so but this is the definition.
Acha, that you are not using.
We are implementing it by a local rule. Okay? We are implementing using a local rule. We are calculating the claim is that this algorithm will actually calculate this function f exactly for any graph, any values of eta you assign, it will give you the correct function f. Okay? But this is done using a local search. But iterated local search. The iterated is important because you cannot do it without iteration, because there are funny paths and they affect somebody else, and that somebody else affects somebody else, and so on and so forth. Okay? Very good. So, no, it's parallel update everywhere. At each time step, everybody is allowed to update his number. But if your friends are reporting 1, then you just have to report 1, you cannot do anything. So you update, but you update to the same value.
But the value will change, like
From the boundary it will change inward, and then from inward it might also affect later the outer one. Because this guy quoted eta, but this time it was quoting 1 here before, so it didn't. But now this guy may quote even lower value than so it might quote a lower value than, these things can affect neighbors later. And in the end you get to a point where nothing is changed, and that actually implements the function exactly. Okay? This is not fully related, but this iterated information which is known to others is a very nice concept which is somewhat subtle, and I will not give you the full thing, but you can read it up. But anyway, there is a story which is the following. There is an island in which there is a finite number of couples, n of them, and it turns out that all the wives are not fully faithful to their husbands, and they are having affairs with somebody else, but the husband doesn't know. Everybody else seems to know that this guy is with this one, but they don't discuss with each other at this point, and the husband doesn't know. Okay, so a new priest comes into the island, and based on whatever, so he says that puts all the people together and says, Howard, can you say something about your wife? So everybody says, my wife is great and very faithful and so on. Everybody says the same thing because they don't know anything else. They know that this wife is not faithful, but he's not asking about that one, he's asking about mine, and I don't know anything against her myself. So this guy says, okay, everybody says my wife is very faithful, everybody says. So then he says, but I know that infidelity is going on in this island, somewhere or the other. Okay? And so then the people start thinking that how can that be? And so, well, nothing happens. So he goes to the next day, he calls all the people and asks them the same question. And no husband can be sure that his own wife is infidel. Right? So they all say the same thing. And then next day and next day. But after n-1 days, the next day he comes and all the husbands have shot their wives. Okay, and this is a story, but the point is, how come in the beginning the information, on what basis did this guy conclude that my wife is infidel on the nth day but not before? So somehow on the last day he says that nobody, if there were at most n-1 infidelities, people would have somehow discovered it less than n-1, so now there must be n, so my wife must also be infidel. You can read up about this logic puzzle in some place or the other, but it's an iterated information. Nobody is directly telling you about your wife, but in the end you are able to conclude, but only after n steps, not before. Okay, up till the n-1 step, everybody said my wife is great, but on the last day, all of them shot their wives. So here also, this is not, it is less gory situation, but the values of f are being changed, and in the end, you are able to get the right answer, even though you start with very wrong answers. Okay, so that is sort of the interest in this problem. Sorry? The zeros don't change because if you are at the boundary, you don't need any eta, you can just be there, you can stay there. So the definition of f is consistent. If you are at the boundary, you don't need any. It is like there is a, when you go through from here to here, at each site you have to show a pass. And if you have a value f, then that guy locally, the toll person, sees, your card says you can go through here. But if the value is less than his threshold, then he says, no, you cannot move, you just stay put. So then, if you have high enough threshold, a good strong card, then you can go through. But less strong, you cannot go through. That is the way to think about this. Okay? So at each site, you will check. If my card is stronger than the local value, then you move on, otherwise you cannot move. Okay, so now I will discuss another problem. So this is the self-organized directed percolation. Self-organized undirected percolation, we have finished discussion actually. So it's the same behavior, and it is obtained by this iterated process of information sharing. Okay, so now I want to introduce a still different problem, but it's a percolation problem, but it's a variation of the percolation problem, and it introduces some new concepts, and there are some ways you can actually answer some of those questions, and that's what we want to discuss. So final example of percolation problems, I will discuss this variation of first passage percolation. So we discussed first passage percolation. First passage percolation was like this. There is a lattice. In the beginning, this is a way of expressing the first passage percolation problem. There is a site, and it can infect a neighbor with rate lambda. Lambda dt is the probability that in the next time step this guy will be infected. So you start with one infected site, everybody else is healthy, but with some probability this guy catches infection. Once it catches infection, it stays infected for in the simplest model. Okay, so after some time this guy will catch infection, this guy will catch infection, this guy will catch, then these guys will infect the next neighbors, and so on. And so if you look at large time t, you will find that some set of neighbors of the given site are infected, some cluster of invaded sites, and other sites are not invaded. So you can see it is not so, the general idea of invasion into something in territory is still there as it was there in invasion percolation, but here the rules are a bit different. Each guy is just invading independently of others. Whether this guy is being invaded or this, they are not worried about each other, they just invade independently. And we are asking that at time t, is this site invaded or not? You know, what is the boundary of the invaded cluster?
But there can be holes also.
Sorry?
There can be holes in the cluster.
There can be holes in the clusters. Okay, so is this site invaded or not? So then it says that from this site, if it is infected in the end, then there is an infection path. This infected that, that infected that, that's how the infection reached. So when this guy got infected, until the time this infection reached here, this is the traversal time of the infection along the bond. And right now we are taking it to be an exponentially distributed random variable, e to the power minus lambda t is the probability that it was still not infected, right? So it's very simple. It is a problem in which each bond has a traversal time which is an exponentially distributed random variable. And we are asking what is the shape of the infected cluster at time t. And we showed you a picture of the Eden model, which was this particular model before. So that is called first passage percolation. Now we will just modify this problem to make it slightly more structured and more complicated. So we will say there are two types of sites. One is called red, and one is called blue, and one is called empty. So red people are called preys, blue are called predators, and E is empty. Okay, so we'll get into the details later, but my general idea is that the prey, if they find some empty site, they go and reproduce there. So they grow by invading the empty sites. And the predators, they eat the prey. So they grow on the prey and keep on eating them. And predators don't die in this model. They just stay put. But they cannot grow. Unless they find somebody to eat, they cannot reproduce. Okay, that is the model. And it is sort of, I think there are all kinds of predator-prey models in the published literature and in ecology and so on and so forth. But we are making a simple caricature model and seeing what happens in that model. So my model is this. There is a single predator and there are preys here. Prey, 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 prey. So this is called blue and these are called red. That is why the names are like that. In my pictures, I will draw blue and red. So there is a single blue site and there are 4 red sites. Now the red sites reproduce, red next to a white, which is empty, changes it to red. At rate lambda 1. Okay, they just reproduce to the neighbors with rate lambda 1. And the blue next to a red.
White on empty sites. So W is empty.
Here.
No, I'm saying that.
Oh, because we will imagine that there is a empty space in which this predator and prey can move.
Is white different from empty or white?
Yeah, white is just neither red nor blue, just empty.
Empty.
Okay, so preys can go to empty sites and occupy them, but the predators have to eat and they cannot occupy empty sites by themselves. Okay, so B next to red changes it to red. At rate lambda 2. So this process is really occurring in continuous time, and lambda 1 and lambda 2 are parameters. I can choose one of them to be 1. Changes it to, blue, sorry, sure. So I will take lambda 1 to be 1 and try to see what happens to this system as a function as I vary lambda 2. The simplest case is lambda 2 equal to 0. Then the predators don't do anything, they don't move. And so this cluster, just the red grow and grow and grow, is the Eden model. So the red grow outward. The size of the cluster increases linearly with time. We didn't prove this result, but you can take it for granted. I don't know, I can actually try to prove it myself, but I can say if you take time t, it will at least move this much and so on. So you can set up lower and upper bounds on how far the system can go in time t. Okay? So anyway, so suppose lambda 2 is 0, then the cluster of lambda 1, red cluster, will grow and will become bigger and bigger and bigger. Okay, now suppose blue is the lambda 2 is not 0, but it is small. Then what happens is that these reds grow, and then inside the blue start growing, but they grow at a small rate because they are, let us say lambda 2 is less than lambda 1. Then they will grow slowly. By the time this guy reaches here, the red has reached even further. And so the growth is actually quite simple. Each of them is kind of growing independently of the second one. And there is a blue cluster, and outside there is a red cluster, and the red cluster grows faster. So it's not a problem. If lambda 2 is less than lambda 1, this is what will happen eventually, because the reds will grow fast. And so there is some annular growth in which there is a region of red and there is a region of blue, and outside it is empty, and they keep on growing. Right? This is very simple. But what happens if lambda 1 is bigger than lambda 2? Sorry, lambda 2 is bigger than 1. Okay? Then these guys grow fast. In fact, they can grow fast so that they eat up all the red ones. And then they cannot grow either. So they just get stuck. The system gets stuck because all the red get eaten. And the red get eaten because they were eaten before they got chance to reproduce. Okay? So I can imagine that if lambda 2 is big enough, then in the end there will be some blue sites on the lattice, and they will be stuck and nothing will happen. This is correct. This is what happens. This much I figured out without doing too much work, So I realized that if lambda 2 is very small, the behavior is like this. If lambda 2 is very big, then the behavior is this way. But what if lambda 2 is 1.1? Okay. Naively, I might guess that whatever I told you continues to hold all the way until lambda 2 is greater than lambda 1. Because they grow fast and they eat up everybody. No, it doesn't happen. Interestingly, there is a surprise. It says that for lambda 2 less than lambda 2 star, reds can survive forever. So I think this notion, I've written it down like this: reds can survive forever. No particular red survives forever. Eventually, that guy is eaten up by a blue, but his children survive. So that is good enough for me. I don't have to survive myself so long as my children survive. So some or the other red survive. That's what is meant by red survive. Means there are some red sites even at very large times. Okay, and of course it doesn't happen all the time, because even if this was the system, this is a stochastic growth. So this red is here. It can grow with some rate, but maybe it didn't grow. Then there was a local alarm clock which didn't fire, and this was eaten up before this guy grew anything. Okay, with some probability that happens. And this was also eaten up, and everything was eaten up, even though lambda 2 was less than lambda 1. With some probability, you can go into a finite state, even though lambda 2 is less than lambda 1. Okay? But with a large probability, it will keep on growing. This is a typical behavior, or typical behavior means with some probability bigger than 0, the red survive forever. Okay, that is the claim. And the cluster of red has a radius which is infinite. But this point is very surprising. In fact, it turns out that lambda 2 star is nearly equal to 2. So even if the prey invade at a rate which is twice the rate at which the reds can grow, they can survive forever. This is what is found. People can simulate this, so they simulated it, and they found that the reds survive forever, even when lambda 2 is substantially bigger than lambda 1. They don't survive if lambda 2 is much, much bigger, but they survive if it is only 2 times bigger. So how can that happen? This is what we want to understand. Okay? Yeah. Everybody is infecting others independently of each other. Okay? So if this guy can eat this and this, both of them it has a local clock which it will eat this one, and once it has eaten this one, it will also eat that one later or whatever. Every bond can infect the propagation independent of other bonds. Okay, very good. So now, it says if there are no predators, the behavior of the model is quite simple. This is continuous time Eden model. Cluster of red side grows with time, and the diameter of the cluster grows linearly with time. He already said this. If lambda is bigger than the 1, my lambdas have got flipped in the write-up and what I said before. The lambda is the rate of 2 infections, and here lambda is the rate at which the red cluster grows, and this one is 1. This is the new definition of lambda. Is the rate at which the red clusters grow, and the blue grow at rate 1. Okay? So if lambda is much bigger than 1, the red cluster grows with time, and inside it a blue cluster grows at a smaller rate. If lambda is much less than 1, the predators are in a hurry and eat up the prey before they have chance to grow. Then the prey die out, and the predators cannot grow as they need prey to reproduce. Then the system goes into an absorbing state with a non-growing cluster of blue sites in a background of white with no red. We already said all this. I'm just repeating it. Okay, so there will be a critical lambda star such that for lambda less than lambda star, all prey die. For lambda bigger than lambda star, the prey can survive for long times with a non-zero probability. Okay? And the interesting non-obvious point is that lambda star is much less than 1, it is closer to half. How can the prey survive if the predator can move much faster than the prey? So this is sort of the hand-waving explanation. It says the red can survive even in some range of lambda less than 1, as red sites on the average have more white neighbors. So a red site on the boundary has 3 white neighbors. So at least one of them should be infected, then then it can grow. But blue sites can grow only on red sites. So they have often fewer neighbors where they can grow. So they actually grow at a smaller rate, even though the rate is faster. The environment in which they can grow is smaller, and so on the average they have fewer growth sites, and so they grow slower. And so long as these rates, the red rate is bigger than the blue rate, they keep on growing and surviving. That is sort of the qualitative way to understand. Okay. And here is a picture of one of these invaded clusters. And so you see the blue have grown, but at the boundary of the blue region there are some places where there are still red patches. So these red can grow further out, and then they will be eaten up by the blue. And some parts, the red cluster will just die because all of them were eaten up by the blue. But in some other part, the red will grow, and it will grow more than, it will lose. So its size will become bigger. And they keep on jumping from some place to another, and some place or the other, red survive. This is the bottom end point. Okay, so this picture explains qualitatively what actually happens. Inside the blue cluster, there are a lot of holes, which is funny, because here what happened was that this was a white region, but before it could be invaded by red, all the people on the outside were eaten up. Then those white cannot change. So the holes, if they are fully surrounded by blue, they will remain forever. Okay. So now, of course, this picture is very suggestive. It is like some percolation cluster, and can I tell the statistics of this cluster? What is the fraction of blue sites inside or outside, or does this stuff have some fractal dimension or whatever? All kinds of questions related to percolation theory you can ask for this cluster of blue sites. Okay, and I would like to understand them because that might help me understand more complicated situations. Okay, so so this is one phase transition which occurs in this system. There is a lambda star below which red don't survive and above which they survive. Okay, but actually there is an interesting variation of this model in which you see there are two thresholds. One is a directed percolation threshold and one is an undirected percolation threshold. So I will see both thresholds in the same model. So you just want to introduce this variation. And so the evolution, sorry, there is a U missing, evolution occurs with parallel update of all sites. So now we will make a discrete time model in which all sites are updated in parallel. And the rule is this: a white site with a red neighbor at time t becomes red at time t plus 1 with the probability p1. Okay? And a red site with a blue neighbor at time t becomes blue at time t plus 1 with the probability p2. And we will change these parameters p1, p2. These are like lambda 1, lambda 2, but now I am working in discrete time. Okay? And it introduces some extra features which are not present in the continuum time formulation. And this problem has a more complicated phase diagram in the p1, p2 plane. You see all these different structures. So this is p1, this is p2, and I have drawn lots of lines in between. So what are these lines? If you go to one of these regions and you look at large time cluster, it has one qualitative shape and behavior which I can describe in words. If I go to this region, it has a different shape and behavior. And this one is different, and so there are so many different possible shapes. And that is the characterization of the phases, the definition. We haven't given the definition, but I'm just saying there are many different phases. Okay, so what are these different phases? This picture tells you what they are. One phase, I don't know where it occurs just now, but there is one phase in which in the end you only have blue and then there are holes and there are no reds. That is what we discussed before. That is when the reds grow at a very small rate. Okay? There is a case where they both grow and red grows faster than blue, and there is a blue cluster and there is a red cluster and they both grow. And this boundary has a finite thickness, so the red is growing faster than blue. Okay? But there is also another case where the red and blue grow fast at the same rate actually. But at the boundary of blue, there is a few places where there are some reds, but they don't have very thick. There is just a thin layer of reds, and it stays at the boundary. The reds keep on jumping around on the boundary, trying to survive somehow, but they don't have too many, and they are always at the boundary. The thickness of the boundary is small, and the rate of red and blue growth is the same. So if I take the average over lots of realizations, I will find that the red boundary and the blue boundary are actually coincident at large times. So I am distinguishing between this and this and this. That is easy. This is a phase in which red and blue both grow to infinity, but they grow at different rate. This is the case where they grow at the same rate. And this occurs in a finite parameter space. You can change P1 and P2, and this qualitative behavior will not change. It will remain the same. Okay, what about the lower ones? Lower ones are like this one. What is the difference between this and this? Okay, so here what happens is that yes, red is growing, blue is growing. They are growing at different rate. The thickness of red is increasing. But if you look at the red cluster, its shape is different from here. In what way? There is a part which is actually flat. There is a line, and then there is a curved region, and there is a flat part. So the red cluster has a flat segment in it. Boundary of the red cluster has a linear part. Okay, and here there is no linear part. It is all sort of some curved shape. Okay. Yeah.
Last time,
Yeah.
some region will be
Yeah, no, so this is average, and so what you need to do is to draw these clusters at time t, then take the limit t goes to infinity, and this is the velocity as a function of time curves. Velocity as a function of orientation curves, and here the velocity as a function of orientation will be such that there is a flat part. These are averaged over time, so that these time fluctuations are and asymptotic large time limit, so that the fluctuations are much smaller and they can be ignored. Here, this is actually different from this, but here the red and blue both have a flat part. Okay, but in this region they are different. Here the red is growing faster than blue. And here both of them are flat parts and both of them are everywhere coincident. There is a region of parameter space where they will be both coincident, even though both of them have flat parts. So this part, the fact that there is some flat part in the curve is surprising a priori, but it is not really surprising. Yes, sir. Yeah. Yes. This one.
So in this case, the blue clusters grow at the cost of the red. Right? But
Yeah.
The sizes are not comparable.
Sorry?
The sizes are not comparable. So I was thinking, is it possible that maybe we can have a phase separation of red and blue clusters where the sizes are comparable of the two colors?
You can say this, but it doesn't happen. See, I understand. The point I am trying to make is this, that based on your intuition, you are guessing that this is what happens. But your intuition is wrong, it doesn't happen. So what do? You retrain your intuition. You realize that no, this doesn't happen. All of us have to do this all the time. When you were 5-year-old, your intuition was very different from what it is now. Right? So you just have to say that, oh, I thought that you can do this in 1 hour, but when you are 20 years old, you realize, नहीं, उसमें 3 घंटा लग जाएगा. You know, so I'm just saying that, okay, you thought that, but it's wrong. It doesn't happen. So you think again. Instead of trying to find the reason why your intuition was wrong, just fix it so that you realize that it should not happen that way. Okay. Okay. So, yeah, so we were discussing the flat part. So, why is there a flat part in these curves? So, this is what we want to explain first. So, I'm having the same discrete time picture, and this is my blue, and these 4 neighbors are red, and the cluster grows, you know, whatever it does. Now, let us say that P1 is bigger than the directed percolation threshold on the square lattice. Okay? Then, from this point, there is a path which goes like this, which keeps on going. You know, there are some paths, it is not everywhere, but there are some places where there is such a path, it keeps on going. And so, so here, the rate the fluid flows is with velocity 1. The infection flows with velocity 1, which is the maximum possible speed at which it can move in our problem. And that speed is reached for a finite cone direction. If I take P1 bigger than PC directed, then there is a cone in which there is a percolation cluster. Each of these sites here is reached in equal time. And so all these sites will, maybe not all these sites, but a finite fraction of these sites will be reached with maximum velocity. And so the front will move with velocity 1, which is the maximum possible velocity of the system. So there will be a part of the red curve which will move with velocity 1, and in other regions it will move with velocity less than 1. So in the previous graph, there is a PC directed percolation threshold, and there is a vertical line. On the right, some part of the red cluster will move with velocity 1, and on the left it won't move. There won't be any part which moves with velocity 1. If it moves with velocity 1, that front is flat. And the same thing occurs for the blue curve. There are some parts of the blue curve which move with the fastest possible velocity 1, right? And so they will coincide with the red in the flat part. But in some other part, they will not coincide, and the red clusters can still continue to grow. And so that is what is shown. Now we can go back to this picture. Yeah, sorry, here. So here the red was eaten up. Here the red and blue are growing at the same rate. This red boundary is very thin. It is actually it is width 0, but you know there will be some sites which are red and not infected, but blue didn't get there. So there will be some red sites at the boundary. So I'm in this picture, I'm throwing it like this. But in some other directions, the red grow faster than blue. Here all of them are the same. And so that is the end of the discussion, no? So there is this boundary, but on the other end there is also this boundary, which is the flat boundary. For blue is bigger than PC directed, then blue will have a flat front.
Like in the P1 equal to 0.6 case,
Yeah.
there is no white side in the center.
So by definition, in this case, if the, I just drew it like this because I was drawing the velocity, so yeah, with good point. So good point. So what exactly is this curve? This curve is plotting the velocity of the front as a function of orientation. It is not plotting the density of the blue sites inside. Okay. So I'm just saying that if you go in, if you take, say, this point and grow in this direction, this will give you the velocity of the blue front and this will give you the velocity of the red front. Okay. That is what is being plotted, not the density. Okay. So now we have argued that there is a vertical line and there is also a horizontal line which are at the directed percolation threshold of the original, of the just the square lattice. When I defined this problem, I didn't think that lambda 1, lambda 2 will have anything to do with directed percolation, no, but they are, the same directed percolation threshold will work here, and this argument can be extended to other lattices, that is not a problem. But now I just want to come to the last point, which is look at the point E. So there is a boundary of Q0. Q0 is the phase where the clusters are like this, where the blues don't survive. So the boundary of Q0 is the reds start surviving. The boundary of Q0 is where the reds start surviving, and E is the end point of this boundary as a function of P2, when P2 equal to 1. Sorry. Sorry. Yeah. So suppose I consider the case when P2 equal to 1. That's a very interesting special limit, is there that the blue sides always eat up, right? So, but can the red still survive sometimes? The answer is yes. And when? So we will say that suppose I take the initial cluster, then the red have only, they are born at one time, but behind them is the blue front, which is only one time unit away. So the red can survive only for 1 unit of time, and then it just has is eaten up. Okay. In that 1 unit of time, if it can reproduce, that is okay, that is allowed. Then then they can live. Otherwise, not. So we should imagine a process in which there is a red, and in 1 unit of time, it can infect the neighbor, and then it dies. Then then that new babies, they can survive for 1 unit of time, or they are killed. So what you have to imagine is that the path of infection will be a process in which with probability P1 there is a bond present, and if that bond is not present, that thing doesn't happen. If that bond is present, the baby will be born there and it will grow. So what is the threshold at which there is a such bonds of connected infections can go on forever? That is the undirected percolation threshold on that lattice. Right? So end of discussion. So we have proved that the threshold of E is the PC undirected, which we showed was half for the square lattice. Okay? Okay, very good. So point E, the P1 coordinate is the undirected percolation threshold, and we have done this argument, and we have done this. Okay, problems. Can you construct? So we did this for undirected percolation. We found a model in which the system finds its own critical point. It goes to its critical point by itself. It's a little bit of sloppiness involved in these words, but you understand in which sense I mean it. In fact, you can calculate some correlation functions at large times, and they will be related to the correlation functions of the critical percolation problem. Okay, but can I do similar thing for Ising spins, where I start with set of Ising spins, they do something or the other, and the dynamics is such that at long times it becomes the Ising model at its critical point. This problem a lot of people have tried and nobody has managed to do it so far. So percolation is not very different from Ising spin, but it is still different. And for the Ising models, the corresponding generalization is not yet known. Okay, lot of people tried. Well, 5 or 6 people tried, but nobody managed to get it. Okay, so here the second one says that consider this problem chase escape percolation which we defined. So let us go back in this picture. Sorry, what happened? I only went back. I didn't want to see. Okay. So I am in this regime, this one. So there is a red front and there is a blue front. It seems reasonable that the velocity of the red front will be independent of the rate at which the blue spread. Okay, because they are growing and the reds are so blue are so far away, they don't matter. This is actually true, and there is a theorem to this effect. But in this case, what is the velocity of the front? So if the blue is infection rate less than red, then the velocity of the red doesn't depend on the infection rate of blue. But at some point it starts differing. So at the end point of this regime, will the red and blue move with the same velocity or not? Yes, but what is that velocity? Is that the velocity in the without blue being present? In this regime, is the velocity of the red front independent of the velocity of the blue? And the answer is no. The answer is that the red front moves at a smaller speed because there are praise present. So this one is actually, it sounds okay. If I said the other way, you would also have nodded your head. So it's not very clear what actually happens. But actually there are some very interesting theorems in predator-prey kind of models which says if the predator rate is small, then the prey front doesn't care about what the predator does. And those models, that theorem actually doesn't work in this problem. Okay, of course, but that was a theorem, so how can it fail? The answer is the theorem was for continuous time evolution, but we are considering discrete time evolution. So the theorem was not strictly applicable. But if I were to think of the discrete time problem as qualitatively similar to the continuous time problem, I would have expected these kinds of simple theorems to continue to hold in the discrete case, and they don't, and it was not clear why or where the proof fails. Okay, so it turns out that the continuum problem, they write some differential equations for something or the other, and in the discrete case there is no differential equation you can write because you cannot differentiate anything, right? So the reason the proof fails is because in the discrete case you cannot even, the starting point of the proof in the mathematics literature is a differential equation, and in my problem there is no differential equation, so I cannot even start. Okay, this point as a big is a sort of result, but it is there is a lesson to be learned from this, which is that some of these continuum treatments have limited validity and they cannot actually hold in some other problem which the system was not exactly as envisioned in the mathematical proof. You should take those kinds of results of theorems with a little bit of grain of salt. Okay, a bigger discussion of this issue if you want more educated discussion. What happened now? Yeah, your microphone is okay. Can I move this down, or microphone is not working? Anyway, my time is also not working, so this is an automatic shut off. I wanted to just show one more slide and then I will be over. Can you just close this? No, this doesn't work until that window goes closed. Yeah.
No, while they were waiting, I have a quick question.
Sorry?
No, while this is working, I have a quick question.
Yeah.
See, like this red region,
Hmm.
like when the blue is let's say going at the smaller, it's like a hidden model.
Yeah.
that is it.
Yeah.
And this fluctuation is KPC.
Hmm.
Right?
Hmm.
So now what happened as you change lambda when we are
Hmm.
still KPC or it changes?
Yeah. It is still KPZ.
Still,
Yeah.
that
Hmm.
is always KPC.
You just have to look in the right place, then you find KPZ.
The phase diagram,
Hmm.
you know, how does it, some of these phases at least exist in one
Hmm.
dimension? Because, you know, the argument which you give,
Huh.
that is just the undirected percolation, that becomes 1,
Hmm.
but then the directed percolation is still 0.7.
Yeah.
So there are still the other phases
yeah.
would exist in one dimension also.
Yeah. No. One dimension? No. This was in 2D.
No, this was in 2D, but if I extend, you know, does it, some of these features at least exist in 1D?
I think the 1D problem is more trivial. So we can discuss it, but I think it is more trivial because there are not too many paths. Things can only grow like
Achha,
this,
achha,
so
achha.
there are not so many
some-
phases possible.
Yeah, it is not possible.
Hmm.
But I'm just saying that only the top one, T2
Hmm.
equal to 1,
Hmm.
that point will get the corner.
Yeah.
But PCDP is still at 0.7. So then
No, 0.7 क्यों होगा? 1D,
1D, 0.7, PCDP.
PCDP for the 2D problem. No. Let's be careful. So PCDP is what PC? Of what DP?
1 plus 1 DP.
1 plus 1. We will discuss it
Achha, achha.
separately. Okay, can we sort of just do the last? Okay. So this is the set of references, so it's there in the notes. You don't have to scribble them. The references are in the notes, and all these issues are discussed in somewhat more detail in those references. Okay, so I'll stop here.
Okay, so this is the last lecture of the less time because for a wonderful.
Thank you. Okay.